Okay, so hello everyone. So I'm Nicolas Yos, and
I'm Adrien Guinet.
so we'll speak about the challenge that appeared during the Journée du Patrimoine. So it was a really nice time where I spent my weekend with friends, and that was the challenge. And for the first part, the start of the challenge, I will let Adrien speak about it.
So thank you, Nicolas. So the first challenge was named Real World Technography. It actually looked like the Aztec challenge that was also there 2 years ago, I guess. So it's a GIF. So what we do is that we dump, so because I did this challenge 2 years ago, I dump every frame of the GIF, and I knew that there was somehow a comment, I think, that will tell me you should look at this frame, and it actually happened. So you know that you have to look at the frame 114, and it looks like this. So you have the flag in the frame, so that's easy. And maybe you can wonder why you have this. I can do that. I can. Okay, cool. So you have this cross here because 2 years ago you had to change colors to see another QR code, and with this QR code you had the flag, but this one was easier. Anyway. So you go to the second step. You have a web application that looks like this. So basically, it's an application that takes your IP and finds out various data about your internet address. And then you see two things. You have this FAQ which say, "Can I check another IP address?" And it says yes. You just give a HTTP header with the address you want to check, and we do it for you. And then you have this other thing. You see this "is it down?" Which maybe use a ping command or something. So we try this by hand, and what we see is that if we call the EasyDown API, we have this trace which shows the output of a ping command. And so what we do, we use a very elite tool which is called grep, and we search for ping in the source code, and we see that there is a classical command injection vulnerability. So we tried this one with just asking to inspect 127.0.0.1 with ID, and then we see that we have the output of ID in the trace output. So we do a small Python script to automate this, and we ask to dump the slash directory, and we see we have a flag file. So we just cat this flag, and we have a message for tonight CTF that say that this will be much harder.
Then there is the first reverse engineering challenge. So I, of course, used the open source software to solve this challenge because it was during the weekend. So here's Ghidra with some code which is really readable. At the end, we have some functions. So as this is not readable, here the zoomed code. So basically, you malloc some memory, you write things, and then you use strange function make context for context, which are functions from a standard library that basically calls the function which is given as parameter with some kind of context. It's like in order to simulate threads. And this function is basically jumping on a rope chain. So what we had is a rope chain. The functions that are invoked in this rope chain just pop values from the stack and put them in global variables that I called registers. So in BSS segments, there are two locations. I call them A and B, and the gadgets are just popping values into them or incrementing them. And there is a gadget that just compare some offset from the input of the program with the other register, and this is the way that the input of the program is checked. So basically, all what we need to do is to patch the program to change this comparison into a move, and with this we can just generate the flag, print it, and we get directly the flag.
Okay, so next challenge, it's a name BLE everywhere, and it's a PCAP file, so we fire up Wireshark. So if, like me, you've never done BLE in your life, you end up with this because you never configured Wireshark in your life for that. And so you've got, it's not, maybe not readable, but you've got something like this error. Well, actually you can read. We have the DLT 157 thing we need to put in our preference, so we Google that. And what we have is that we need to set up Wireshark to say, oh, this is a Nordic BLE device thing, and this is going to be fine. So you do that, and then you have a readable output. And then you see that you have a device name, which is polyg, muki, something. So you look on the internet and you end up on this. So it's a smart coffee cup, when you can upload a picture via Bluetooth BLE, and it's really cool, and you can put your face and everything. So it's a capture. So it looks like it's a capture of this process that is happening. So if you look on the internet, you find that someone reverse engineering this protocol for you. So what you understand is that there's no encryption in the protocol, and basically what is transferred is a bitmap image with the size which is here. So if you look at the capture, you see that you have these write commands. So which looks like here what we have is that we have a lot of white pixels or black pixels, and some are not black or white. So it looks like we need to dump this, and we'll have the image. So we make a small Scapy script, and we use also a plugin from Sysdream to support the NOR BLE thing. And so what we do is basically we just dump the payload for every write command. We write that in a file. Then we use ImageMagick to generate the image and end up with this. So the first time I just read Bluetooth, not so smart. You can actually try to figure out. And Nicolas sent me his image. Is like, I'm like, oh, this image is really better. So actually you need to reverse the bit order of every byte, and it's really better in the end. All right. So next challenge is an ELF binary. So we have to reverse engineering it. So it looks like to trap me because it just asks for a flag. So I won't show you a lot of GreHack thing. Actually, I will show you any. So if you reverse engineering the thing, there's no obfuscation, there's nothing. So it's actually quite easy. You understand that each character of the flag makes you move in some kind of maze. And you need to go from one place of the maze, which is X, to the end, which is there in red. And so you need to figure out the flag to move through this maze, to end up in the good place. So each character is split into two tuples of 2 bits. So it's 4 movements per character. If you reverse engineer, you understand this table. And so you have 2 possibilities to figure out this flag. You can make an automatic script that will brute force the thing to find all the various possible ways that you can do. Or you can do this by hand like I did, and you write, you need to go to this direction, and all this thing, and you dump the flag, and it leads the way with a V instead of the W. Anyway, so next, the final one.
So the final challenge, which is a reverse engineering challenge with many steps. So that's why we are half of the presentation. This challenge has 2 files, the puzzle, and an encrypted script. When we perform dump, it's really random data, so it's encrypted. So just start reversing the puzzle. The main functions are some nice strings. So there's the usage. So the program takes 2 arguments, a file, a DS file, and a key, which is an optional argument. The file name is checked so that it needs to end with .debugging script extension. So it's kind of a debugging script. Then there is the length of the key, which is compared with this file, and then the main process forks, the child process sleeps a little bit, and then calls another function. And while the child process does this, the parent process attaches the child with ptrace, then decodes the key, do things, and just I just analyze what the parent did. Because the child process with the function that is called, it's code that is not real code. So I understood that the parent process is kind of modifying the child process before the child process gets a chance to run the real code. So now the question is, the parent process parses a file. What does this file look like? For this, there is a grammar. So grammar has 2 parts. There is a tokenizer and then a parser. For the tokenizer, there are several tokens, and what's nice is that in the binary there are these strings that directly specify the meaning of each enumeration, of each value of enumeration. So in the grammar we have integer, we have some operators, parentheses, register, and end. In the file, you understand that it parses blocks. in order to have the kind of function. And then there are 10 instructions, B, BH, C, and so on. And sometimes this operator takes parameter, and we have a parser for all of this. When these options take register, it uses Pwners in order to get the x86 register from the child process, and also there are other operations that use Pwners set threads in order to move back some values into the child process. So it's like a real debugger. Here are the 10 instructions, so you can define a breakpoint. The first instruction is when the breakpoint is hit, there is a callback in the child process that is called. The second one, there are callbacks, but in the begin and blocks that are defined in a script. And it continue, there are some writes. FZ, it's flip ZF, so that in the code you have conditional jumps, but in fact, using the debugging script, the condition is inverted. That's quite nice for an obfuscation. There are other things, there are also mem copy, so so far we have seen that the program is interpreting some kind of a GDB string. It's not GDB, but it's kind of. We don't have this script, but it runs on a child process. So the challenge consists in writing the script. It's kind of weird. In the program, there is another function which is not referenced anywhere, but it exists, that decrypts something with an algorithm which should charge RC4. It's not exactly RC4, but it's a decryption encryption algorithm. Maybe. Was thinking it was Saturday night. There is a debugging script which is embedded in the process. It's not the case, but I was thinking this. So I tried to reverse engineer this function. It's root for some things, and in fact, it's a function that decrypts other function. And now I go back to the child process. The child process sleeps and then run a function. And in fact, this function which is run is encrypted using this function. So the binary embeds 500 keys, and it finds the key that encrypts the function well. With this, we can decrypt some code, which is nice. So yeah, that's content on the slide. So the function 15AD is encrypted. We can decrypt it, and so we can follow up. But it calls other functions that are also encrypted. How can we find all the functions that are encrypted? And there is a nice thing in this binary, which was the dwarf symbols. So with one command, you can just dump all the functions that were compiled into the binary. And using some heuristics, we can find functions that were encrypted, decrypt them, write them back into the binary, and with this, we have decrypted every functions. But the thing is, so this is the function that is called from the main program, well, the first child process. The first 4 instructions are normal. It's the function prologue. Then there is a conditional jump, which is kind of strange because it jumps before the function, and then it's just garbage. It's really weird. Well, maybe we need to write a debugging script that jumps a little bit later, because later the instructions are nicer, but it's kind of strange. So far, the main program forks a child, while the parents debug the child, perform some things. There are functions that are encrypted, but I haven't seen where this decryption is set up, and it's kind of strange. So now let's go back to a second file, script.ench. It may be encrypted with one of the keys that are encrypted, but no. So let's try to brute force. It was like Sunday morning, 2 a.m. Let's try brute forcing the encryption key. And well, after some seconds, it succeeded. Very surprising. So the encryption key was really short, which was in fact, I misread the code. The main instruction just compare, and it requires a key of 4 bytes, which are then base 64 decoded. So it's really fast to brute force. And with this, we can decrypt the script, which is a debugging script which follows the grammar that I understood. The script look at this. So there are many lines that have expressions. Here I define some blocks, I define breakpoints, and so we need to simplify this. Thankfully, so I implemented things to simplify. Among the lines, there is this line, which defines a breakpoint on the first function of the child process that calls the function that decrypts it. So this is how the function that decrypts other function is called with a breakpoint. Then 12 bytes later, there's another breakpoint which is implemented with blocks, so that when this breakpoint is hit, there is a block which is run, and this block just moves RRP, the instruction pointer, 12 bytes later. So it's like a rate of jump in order to skip the invalid instructions. And in fact, there are two blocks, and the second one is really nice, because if you are familiar with machine code like me, the AB0C is a relative jump, non-conditional jump. In fact, the debugging script already implements the code that is necessary to patch the program. That leads to this slide. This is the code which is decrypted, the code after the patch, which is written in the debugging script. And with this, we can have nicer code. With GreHack, we can decompile it, and we have a nice function that can be analyzed. There are many other things that are done in the debugging scripts. For example, there are some values that are hardwired. So I wrote a Python script that just moved the value and creates a new unobfuscated file. There are also like data that are written on some handlers and then written back into the memory. So it was quite complex, but in the end, we have a nice binary that can be analyzed statically. And now it's time for the next part of the challenge. So we have a binary that forces the parent about the child, and the child do this. It first checks a number variable, and then it calls a function. Then it does something weird with this program cannot be run in DOS mode. In fact, the function that is called is to initialize a cryptographic state for the encryption algorithm, which is then used to decrypt things. Then it creates a stream. We know that it's a stream because it's called fclose from the file itself, so argv0. So really weird thing. And then there are some functions that are quite usual when you are performing a track me challenge, and you need to find the flag from a track me program. When we take a look at the first function, the 1052-4e, it takes a screenshot. So you open the X11 display, and then you take a screenshot to convert it with bitmap. So here it's a real simplification, because in fact the function to convert to bitmap is some 5 or 6 functions that are called, and you understand after looking at them that they just create a bitmap. So this function creates a bitmap. The second one opens the file and then decrypts something which is appended to the file. So the function just jumps 4 bytes from the end of the files, read a size, then jumps before and reads an encrypted payload, which is then decrypted. And this payload consists in a binary tree. In this tree, there are two kinds of nodes, the interleaves and the leaf. The intermediate nodes contain some offsets from the image and bitmap images associated with characters, so it's quite complex. So I wrote a Python script in order to represent what the tree looked like. It was quite big, and it looked like this. So there's a root node with character E, position 0, 0, that are 2 children. This node have 2 children, left and right. And then when you go down, finally you find a leaf which have 3 images associated with characters A, hash, and H. And then there are other characters, so here you no longer understand what the program does. So let's go back to this. So here we have a function that creates a screenshot. You have a function that loads a tree of images. And then for the first if, you have another function that takes the screenshot on the tree as parameters. What does this function do? Well, here I slept. I enjoyed the Journée du Patrimoine, and then on Sunday night, I just went back to a challenge, and it was just an OCR, so you just decode a string of characters, and then there's a checker that just hashes the result of the OCR, compare SHA 256, obfuscated, but with John the Ripper, we can find the flag. But in fact, so I submitted it, it was not the flag, because in fact, each images were not the characters, but they were associated with characters. So in the end, the final flag of the challenge was this one. In summary, in this country, mini protection of retail, and that's it. Now, do you have any questions?
C'est marrant parce que j'ai vraiment pas fait comme ça, quoi.
Ouais.
J'ai écrit le script, en fait, j'ai fait un script de GDB. C'est pareil, en fait, en passant, tu vois. Et après, j'ai tout dumpé dynamiquement, en fait. Tu vois, un gros de coordonnées, et boum.
I have a question here. What would have happened if you didn't have the dwarf information in the binary?
Well, with the debugging script, you have all the offsets with breakpoints with the file, where the function that decrypts the function is called. Then it's just hard to find the end of function, but there is a heuristic that I wrote. You can find the end.
Breakpoint at the end.
Well, there is a breakpoint, but also it's there. In fact, the decryption function stops when he sees 3 nops. Then he continues the return until he finds a ret. So I guess that the challenge was written in assembly language, so that at the end of each function there were like 10 nops and then a ret to mark the end of the function.
Okay, so thank you very much.